Hi, in this video we are going to talk about Stack's abstract data type, and we are going to implement it with the help of linked lists. So I'm going to create a new package for the Stack linked list, for example. We have to create a node. It's going to be the node in the linked list basically. So this is for the linked list itself. Then I'm going to have the stack, and then I'm going to have an application.java from which we are going to test our application. So what about the node class? Of course, we would like to make it as generic as possible because we would like to store integers, doubles, strings, and custom objects just for an operating system, for example. So that's why I'm going to use this t parameter and extends the bounded type parameter comparable. We would like to store items that can be compared. Okay, because we would like to decide that whether the given item we store in a stack is smaller or greater than another item in the stack. Okay, so I have the private t data, and of course we have the private node next node. In the node constructor, I'm just going to get the data itself. So the data, this.data is equal to the data. I'm going to override the toString method, and I'm just going to return this.data.toString. It is approximately the same as we have seen for the implementation of linked list. Right click, source, generate getters and setters for the data and for the node. Ctrl+Shift+F to ortho format on Windows operating system, and let's save it. Okay, so what about the stack.java? Basically, I'm just going to make it generic as well. So the t and the bounded type parameter, the comparable with the t parameter. We are going to store a reference to the root node. So the root of the stack. Okay, and of course I'm going to have, just count to be able to track the size of the stack. I'm going to have a public void push method with a t new data. Okay, basically we just have to increment the counter, so counter ++. It is quite dynamic because we implement it with the help of a linked list. And for the linked list, we don't have to check the size like we would do it with arrays. So that's why we are able to grow this stack organically. It's very dynamic implementation. So we just have to increment the counter. We have to check whether this is the first item we would like to insert. If the root is equal to null, it means that this is the first item. So we just have to instantiate the root node with the new data. Okay, I can get rid of this. Okay, as we know for certain that is not going to be the first item in the stack, which means that we have already pushed some items to the stack. So I'm just going to update the references. We have the old root, which is equal to the root. Then I'm going to have this.root is equal to a new node with new data. And then I'm just going to update the references. So the root.set next node is equal to the old root. Basically, this is what we have been discussing in the linked list, that basically this operation is inserting items at the beginning of the linked list. And because we just have to update the references, okay, we have to create some new node, but we just have to update the references. That's why this push operation is going to have ordo 1, so constant time complexity. Okay, now what about the size? The public integer size is just going to return the count. Of course, it has ordo 1, so constant time complexity as well. We can have the public boolean is empty. Basically just going to return whether the root is equal to null or not. It's a very, very fast operation again, so it's going to have order 1 time complexity as well. And what about the pop method? Basically, it's just going to return the data itself. I'm going to call it pop. I have the item to pop, which is equal to the this.root.getData. And I'm going to update the references. So this.root is equal to this.root.getNextNode. I'm going to decrement the counter. Okay. And I'm going to return the item to pop. This operation again has the running time order 1 constant time complexity. So that's the main advantage of implementing stack abstract data type with the help of linked list, because we can implement all the methods in constant time complexity. Okay, you may pose the question that what's the disadvantage? The disadvantage is the memory complexity, because we have to store several nodes, because in the node class we store a reference to the next node in the linked list. So basically that's why I don't want to repeat myself over and over again, but it's very important to see that there's a trade-off between running time of an algorithm and the memory complexity of an algorithm. Usually, if we want to make an algorithm fast, then we have to store several references, for example, nodes and so on. So it's not going to be memory friendly. If we want to make an application memory friendly, then it's not going to be the fastest algorithm possible. For example, let's consider Dijkstra shortest path algorithm. If we wouldn't use a priority queue, okay, it would be memory friendlier, but on the other hand, it would be slower. So there's a trade-off between running time and memory complexity for most of the cases. But here, if we implement stack with the help of linked list, then it's going to work fine for all the operations. Will have order 1 constant time complexity, which is very, very favorable. In the next video, we are going to test our application. Thanks for watching.